Bronsted-Lowry concept of acids and bases. This is the second type or the concept of explaining the acids and the bases. Now, according to this Bronsted-Lowry concept, acids are the species which donates H plus ions. That's it. So, no restriction of medium. Any species which gives H plus ions will be called Bronsted acid. Similarly, bases, the species which accepts H plus ions are called Bronsted bases. So, there is a change. According to Arrhenius, the species which gives OH minus are called bases, whereas according to the Bronsted concept, bases are the species which accepts H plus ions. So, they are proton acceptors. We call them proton, which is H plus ion acceptors, and these are called proton donors. That's the basic difference. And there is no restriction of any medium. So, we were able to classify many species into this, and moreover, the definition of the bases has been broadened now. It has been given a more wide range. So, more compounds has been included into the category of bases. But for acids, it's not much difference. Only the thing is, the advantage is that the restriction of the medium has been completely taken off. The example of the acids whom we will call Bronsted acids will be your HCl, HBr, Hi, HNO3, H2SO4 sulfuric acid, H3PO4 phosphoric acid, HClO4 perchloric acid, etc. So, all these will be your Bronsted acid. So, what similarity we find is all Bronsted acids and Arrhenius acid. What similarity do you find? The similarity is that the all Arrhenius acids will be Bronsted acids, but all Bronsted acids will not be the Arrhenius acid, because the moment the medium is not the aqueous, it will be a Bronsted acid, but according to the Arrhenius definition, it won't be a Arrhenius acid. Similarly, the Bronsted bases will include primary amines, secondary amines, alcohol, water, ammonia, ethers, etc. All these are proton acceptors. These species have a kind of a central atom, which is either nitrogen or oxygen, on which we find that there are lone pairs. Due to these lone pairs, all these becomes what? Very good proton acceptors, because these lone pairs are donated to the proton by dative bond, coordinate bond, and this is how they become very good Bronsted bases. Let me show you this by an example. But like a nitric acid, when added to water, forms H3O plus and NO3 minus. Now, this was also liquid. This is what we have as aqueous. This is what we have as aqueous. if you see this reaction, this particular reaction carefully, what you will find, this nitric acid is the one which is giving H plus ion to this water. Since it's a proton donor, it will be called Bronsted acid. Water here is accepting this H plus ion, so it will be called a Bronsted base. It gets converted to this hydronium ion, and nitric acid gets converted to nitrate ion. So we were able to classify water-like molecules as bases also. Now what you find from these example of bases and this reaction, that these Bronsted bases are very different from the Arrhenius bases because they are not having any OH plus ions. They can't give any OH plus ions. So Arrhenius bases and Bronsted bases are completely two different concepts. These are proton acceptors, whereas Arrhenius bases are the hydroxyl ion donors. Now let us take one more example in order to make you understand that not only the water, we can even classify the amines also as the Bronsted bases. Like if suppose we have HClO4, when reacted with ammonia, it forms ClO4 minus and forms NH4 plus. Now in this you can see this is giving H plus to this ammonia, so it will be your acid. Ammonia is accepting H plus ion, so it's a base. It gets converted to your perchlorate ion, and ammonia gets converted to ammonium ion. So this ammonia, since it is accepting H plus ion, it's called a Bronsted base. So therefore from these two examples and from the different examples which we have done for the acids and the bases, it is very clear that how these Bronsted acids are different from the Arrhenius acids and bases. Now after understanding the Bronsted acids and bases and the examples, we must understand another important advantage of this concept. This concept gave us a term called conjugate acid-base pair. What is exactly this conjugate acid-base pair is? For this, you first need to understand what exactly this conjugate acid-base is. Now, conjugate acid-base and acid and base are the species which differ by H plus ions. There is only difference of H plus ions between the two species. Bronsted gave another important thing. He was the first one who said that the acids and bases dissociation also involves equilibrium. And then by giving the concept of the conjugate acid-base pair, he gave us a very valuable information by the use of which we were able to classify the acids and bases on the basis of their strength as the strong acids or of strong bases, weak acids or a weak base. But first, before doing this, the classifying the acids and bases according to their strength, we must understand what exactly this conjugate acid-base pair is. Now let me give you an example. Like we have taken HCl in water. Now this is a gas allowed to pass through water. The HCl turns to Cl minus aqueous and water turns to H3O plus. Now you need to listen to this first. HCl here is a species which is giving H plus ion to the water, so it will be called an acid. Water here is accepting H plus ion, so it's called a base. Now whenever we put this sign of equilibrium here, it means these two ions can react with each other and can form the HCl and the water back. And if this is the case, it means what? When the reaction is moving in the backward direction, which out of these two species is going to lose the H plus ions? It is this H3O plus. So in the reverse direction, your hydronium ion is the acid because it is going to give the H plus ion, and in the reverse direction, the species which is going to accept the H plus ion will be your Cl minus ion, so it is going to be your base. So what we say is this HCl, which is an acid, is having this Cl minus as its conjugate base, and this water, which is a base here, is having this hydronium ion as its conjugate acid. So this is how every acid has a conjugate base, every base has a conjugate acid, and these acid base pair only differs by H plus ion. Like see here, HCl and Cl minus, this is an acid, its conjugate base, they differ by H plus ion. Water and H3O plus, these two are again our conjugate acid base pair. It's a base, it's an acid, they differ by H plus ion. So this is how we have the acid base, conjugate acid base pair concept. Let us take some other example, like when nitric acid is reacted with ammonia, it forms nitrate ion and ammonium ion. Now in this nitric acid, since it is losing H plus ion to the ammonia, will be called an acid. Ammonia is accepting H plus ion, so it will be called a base. And as we have done this concept of conjugate acid and base, this nitrate ion will be called conjugate base of nitric acid, and ammonium ion will be called conjugate acid of ammonia. The reason is because while coming back, this is the species which is going to give H plus ion to the nitrate ion. So HNO3 and your nitrate ion are the examples of acid and its conjugate base, which differs by H plus ion. Similarly, ammonia and NH4 are the example of a base and its conjugate acid, which differs by H plus ion. So this is how we have a concept of conjugate acid and a base. Now according to this concept, we use this concept to explain the strength of the acids and the bases, and accordingly we were able to classify acids and bases as strong acids and weak acids, strong bases and weak bases. Now let me take you to this in detail. Suppose we have like HCl. We have taken it in water, and we have taken, of course, like suppose another example, H2CO3, carbonic acid. It has also been taken into water. We know what will happen is it will form Cl minus ion, it will form carbonate ion, we'll make it 2, carbonate ion and H3O plus ion. Now what happens is, out of these two acids, both of these are acting as an acid, giving H plus ions, forming hydronium ion. These both are Bronsted acids. Water in both these cases is acting as a Bronsted base. The question comes is, which out of these two is a stronger acid? How can we know this? By clearly, what? On the basis of the value of the equilibrium constant. And we know, Lee-Chatter's principle, more stable will be this conjugate base of these acids. More easily the system will move in the right direction. Larger will be the value of K equilibrium. So out of these two, the acid which has a larger value of K equilibrium will be the stronger acid, and accordingly we say the more stable is its conjugate base, because then only the system is moving towards more stability or in the forward direction. So it is the stability of the conjugate base or a conjugate acid which decides the strength of the acid or a base. Strength of an acid and a base can easily be explained on the basis of this Bronsted concept. Always remember that the strength of acid or a base is directly proportional to the stability of its conjugate acid or a base. More stable is your conjugate acid, the stronger will be the acid. Less stable is your conjugate acid, lesser will be the stability of strength of the acid. More stable is your conjugate base, stronger is your strength of the base. Lesser is the stability of the conjugate base, the lesser is the strength of the base. So it is very much directly proportional, because more stronger or more stable is your conjugate acid or the base, more easily the equilibrium shifts towards the forward side, and therefore the strength of the acid and base gets accordingly increased. What we write simply is, therefore an acid, since it gives H plus ion and it gives, if it's a strong acid, it will have a very stable conjugate base. This is what is most important. Now this stable conjugate base will be a poor base. Remember, these two terms are different. Don't get confused, because it has to have a very poor basic nature, because it will not going to accept this H plus ion. If it's a strong base, remember, if it's a strong base, it will accept this H plus ions immediately and will form this acid back. So in that case, the acid will not dissociate, and this acid will be a weak acid. And remember, for weak acids which gives H plus ion, the lesser stable is the conjugate base, which will be a strong base. It has to be a strong base. The reason is because it will immediately accept this H plus ions and will form the weak acid back. So every strong acid has a very stable conjugate base, which is poor base. Every weak acid has a very strong base, which is actually not very strong conjugate base, very not stable conjugate base. Similarly, the base, if it is a strong base and it is accepting this H plus ion, will have a very stable conjugate acid, very stable acid, which will be a poor acid, because if it is poor, then only it is not giving this H plus ion. If it is a strong, it will give H plus ion, will turn back to this base. And the weak base, since it accepts H plus ion, will have a lesser stable conjugate acid, which will be a strong acid. It will immediately give H plus ion and will form the weak base back. So this is how accordingly we can actually compare these acidic or basic strengths of the different acids and the bases. And on the basis of this, we are able to classify the acids and bases as strong acids, strong bases, weak acids, and weak bases. Like, let me give you an example. According to, after going through this concept and accordingly classifying the system, we can now name certain strong acids and strong bases and weak acids and weak bases.